Today's class I'm going to solve few problems based on Wilson's theorem and Fermat's theorem, and later we'll discuss about Euler's phi function. So one problem I have solved in my last video. I'll take up this second problem. Show that 18 factorial is congruent to minus 1 mod 437. Okay, see, whenever large numbers are given over here, you try to split it as a product of relatively prime integers so that you can easily solve them. Okay, so this 437 I can write it as 19 into 23. You can observe that they are relatively prime. Okay, so when they are relatively prime, we just need to show now that both of them divide 18 factorial plus 1. Okay, then it just means that it is true. Okay, so from Wilson's theorem, I can say 18 factorial is congruent to minus 1 mod 19, right? P minus 1 factorial is congruent to minus 1 mod P. Okay, I'm using that and I can directly write this. Now I need to show that 18 factorial is congruent to minus 1 mod 23. This I have to show now. Okay, for that 18 factorial, see, I'm writing 18 factorial as, say, this is nothing but 1 into 2 into 3, like that up to 18, right? Now I'm combining the terms and writing with respect to mod 23. Okay, so I'm writing like this: 2 into 23, sorry, 2 into 12 in fact, 2 into 12, 3 into 8, 4 into 6, 5 into 14, into 7 into 10, into 13 into 16, into 9 into 18, and 11 into 15 into 17. Okay, now you observe this is 24, which is congruent to 1 mod 23. This is 24 congruent to 1 mod. So again, this you can observe, okay, and you can check it out. This is nothing but 1 power 7 into this product. This is also congruent to 1 mod 23. Therefore, this product is 2805. I have already calculated, so I'm writing directly. Okay. Now this I can write it as this 2805. I can write it as 121 into 23 plus 22, because this 121 into 23 comes out to be 2783. If I add 22 to this, it becomes 2805. Okay, so when you take up this is congruent to 1 mod 23 because it's a multiple of 23. Okay, so this is congruent to 1 mod 23, and I'm taking directly 22 mod 23, which will comes out to be 18 factorial is congruent to 22 is nothing but minus 1 mod 23, and it means that 23 divides 18 factorial plus 1. Okay, since 9 and 23 are relatively prime, okay, so the product also divides 18 factorial plus 1. Therefore, 9 into 23 divides 18 factorial plus 1, and 437 divides 18 factorial plus 1. It just implies 18 factorial is congruent to minus 1 mod 437. Let us look at the second problem. Second problem says, prove that an integer n greater than 1 is prime if and only if n minus 2 factorial is congruent to 1 mod n. Okay, it's two-way proof. Okay, so let us take the first part. If it is prime, then I have to end up here by proving this. Okay, first part, if n is prime, then by Wilson's theorem I can write n minus 2 factorial is congruent to 1 mod n. Sorry, n minus 1 factorial is congruent to minus 1 mod n. That is from Wilson's theorem. Now this is same as writing n minus 1 factorial is congruent to n minus 1 mod n. Right? I can take it as a positive integer. Okay. Now I'll take up this to this side. N minus 1 factorial to this side. It becomes minus n plus 1 is congruent to 0 mod n. I'll rearrange this. Minus n minus 1 is congruent to 0 mod n. I'm taking minus sign outside, so minus n plus 1. Now from these two terms, I'm taking n minus 1 outside. Okay, so inside the bracket, I'm going to get n minus 2 factorial. And n minus 1 I had taken outside. Minus 1 is congruent to 0 mod n. We know n minus 1 is congruent to minus 1 mod n. Right. So this n minus 1 into n minus 2 factorial minus 1 is can be written as minus 1 into this. So sign changes. 1 minus n minus 2 factorial is congruent to 0 mod n. So this is same as writing n minus 2 factorial is congruent to 1 mod n. That is what we have to prove. Right? I hope you understood. This n minus 1 is minus 1 mod n. Okay, so if I take it over here for this, so the sign changes. 1 minus n minus 2 factorial congruent to 0 mod n. Now I'll just rearrange this over here so that it is n minus 2 factorial is congruent to 1 mod n. Then the converse part, I have to take up this. Okay, let n is greater than 1 and n minus 2 factorial is congruent to 1 mod n. Now I don't know what is n, whether it is prime or not, I don't know. Okay, if n is prime, composite number, what happens? It should have a divisor, composite, then each divisor, say k of n satisfies the condition thus k is less than or equal to n by 2 and this k is also less than n minus 2 because it is a divisor of n. When it has got a divisor, say k into something is n, then that k must be less than half of this, and that when I must take out 2 from that, it should be less than that. Okay, it satisfies this. This is because of the conjecture. See, I'll write it down. From the conjecture, thus n must be greater than 4 because when n equal to 2 and 3, they are not composite number, and when n becomes 4, say n equal to 2 and 3, they are not a composite number, right? And when n equal to 4, it does not satisfy this condition. Okay, does not satisfy the condition, so that won't come. So n has to be greater than 4, so that what happens, n divides n minus 2 factorial, and it just implies n minus 2 factorial is congruent to 0 mod n, which is the contradiction to the fact that n minus 2 factorial is congruent to 1 mod n. Therefore, n has to be prime. That is what you have to prove. N is prime if and only if this is true. When this is true, I'll just assume that it is a composite number and it has got a divisor, and that divisor is in such a way that it is less than half of n value and it is less than n minus 2. Okay, this n now has to be greater than 4 because if 2 and 3, then they are not composite. When it becomes 4, it does not satisfy the condition. Therefore, it has to be greater than 4. So when that is the case, n, of course, n divides n minus 2 factorial, and in that case n minus 2 factorial is congruent to 0 mod n, right? Therefore, which is a contradiction, n minus 2 factorial is congruent to 1 mod n, therefore n has to be prime number. Just look at the next problem. It says, verify that 4 into 29 factorial plus 5 factorial is divisible by 31. Now it's 29 factorial, right? So from Wilson's theorem, I can write with respect to mod 31. So I can write 30 factorial is congruent to minus 1 mod 31. Now 30 factorial, I can write it as 30 into 29 factorial, right? So I'll write 30 factorial is congruent to 30 into 29 factorial. 30 is congruent to minus 1 mod 31. So minus 1 29 factorial mod 31. Now this minus 129 factorial is congruent to minus 1 mod 31. And this I'm writing 30 factorial as minus 129 factorial. Over here 30 factorial, I'm replacing it by minus 1 into 29 factorial, which is congruent to minus 1 mod 31. Okay, I hope you got it. Now I'll just cancel minus 1, so that I'm getting 29 factorial is congruent to 1 mod 31. It is 4 into 29 factorial, right? 4 into 29 factorial. So 4 into 29 factorial is nothing but 4 into 1, that is 4 mod 31. Next I want 5 factorial. So 5 factorial, I can write it as 5 into 4 into 3 into 2 into 1, which is nothing but 24 into 5, it's 120, which is 27, yeah, it's 27 mod 31. So I can directly write 5 factorial is congruent to, difference is minus 4 mod 31. Okay, so this I got, I'll add up. Therefore 4 into 29 factorial plus 5 factorial is congruent to 4 minus 4 mod 31. So it becomes 0 mod 31. Therefore you can say that 31 divides 4 into 29 factorial plus 5 factorial. Now let us move to new topic in number theory, that is Euler's phi function. It's part of the theory arising out of the result known as Euler's generalization of Fermat's theorem. So while learning this, we are introducing new important number theoretic function, which is Euler's phi function. Okay, it is described as for n greater than or equal to 1. The notation is like this. Let phi of n, it denotes the number of positive integers, not exceeding n, that are relatively prime to n, See, I'm listing out phi of n is a function. It denotes number of positive integers, okay, set of positive integers which does not exceed n, and those numbers are relatively prime to n. Okay, I'll describe this with an example. Suppose n is 30, okay, n is 30 and you have to calculate phi of 30. So you have to list out all those integers, positive integers less than 30, which are relatively prime to 30. Okay, 1, okay, 2 when I take, it is not relatively prime to 30. 2 I cannot take, 3 I cannot, 4 I cannot, 5 again not possible, 6 not possible. When I look at 7, then they are relatively prime. Similarly 11, 13, you can check it out. 19, 20 is not possible, 21 not possible, 22 again not possible, 23, 24 not, 25 not possible, 26, 27, again they have got 3 as common factor, okay, not possible, 28 not possible, next is 29, yeah, I'm done. So how many such numbers are possible? 1, 2, 3, 4, 5, 6, 7, 8. So 5 of 30 is 8. First thing is you have to list out all the numbers less than n which are relatively prime to n and count them and write it. Okay, so this is 5 of n. You can notice that if n is 1, 5 of 1, this is 1. Okay, because GCD of 1 and 1 is 1, they are relatively prime. Okay, and one more thing you know, you can observe that if n is prime, okay, if n is a prime number, then every integer less than n is relatively prime to it. Therefore, what happens is I can just write phi of n is nothing but n minus 1. This you can check it out with an example, okay? And on the other hand, if n is composite, okay, and is of course is greater than 1, then n has a divisor, okay? It should have a divisor, say d. N has a divisor d in such a way that it must be less than n and greater than 1. And I can say when it is a divisor, then there exist at least 2 integers between 1 to n that are not relatively prime to n, right? Because it has got a divisor. When a composite number is there, I can write them as product of 2 integers, okay? So those 2 integers are not relatively prime to n in fact, okay, because they are the divisors of n. So I can write there exist at least 2 integers between 1 and n, or among 1, 2 up to n, that are not relatively prime to n, namely d and n itself. Okay, therefore if n is composite, phi of n must be less than or equal to n minus 2. There are n integers. Since it's a composite number, it has got a divisor, so they are not relatively, there exist at least 2 integers, they are not relatively prime to n. So that integer is d and n itself, so I can just remove them from this set. One divisor somewhere here and n, I'm removing them, so the remaining is n minus 2. So at the most n minus 2 is a possible value for phi of n if n is composite number. Therefore I can write for n greater than 1, phi of n is n minus 1 if and only if n is prime. Okay, this result is very important. Please keep it in mind, and it helps in solving most of the problems. In my next video, I'm going to discuss about prime power factorization. Thank you.